Hello everyone, I'm Dipmanita. Welcome to the 8th interaction session of network analysis. So in this session, we'll be looking at a few dependent sources and how these dependent sources are connected in a circuit, and all the network theorems, for example, the Thevenin's theorem, the superposition theorem, etc., all the network theorems, how they are applicable to such circuits. So with respect to the dependent sources, like there can be four type of dependent sources. uh, Let me just okay, so it could be these dependent sources are denoted by square symbols, as you must have already know. So it could be a current source which depends on some other current. This I may be the current flowing in a certain other part of the branch of this entire circuit. So if this is a circuit, somewhere in the circuit this current I is flowing, and this current source depends on this particular current. So this is current dependent current source. There could be current dependent voltage source, in which it will be some k dash into V. This V will be some voltage at certain parameters of the branch. These two types of current like dependent current source are present, and in case of voltage source, it could be a current dependent voltage source, in which the voltage, let's say alpha, this will be some constant into some current that is flowing in a circuit. Or it could be voltage dependent voltage source, in which the voltage here depends on some alpha dash into voltage. This voltage is certain branch voltage or voltage across certain elements in the circuit. So these are basically the four different types of dependent sources. So we will solve a few of the circuit problems, and we will look into the Thevenin's theorem and superposition theorem in those circuits. So the first question that we have for today is, a circuit is given in which there is one independent sources, which is denoted by this round 2 volt, and two dependent sources. This is the current dependent voltage source because it depends on some V1. And where is V1? V1 is the voltage across this 6 ohm resistor, which is given as like this, plus minus V1. So when the voltage across the 6 ohm resistance, if it changes in a circuit, this source current, the current source will change accordingly. And it is also connected with a current dependent voltage source, where this current I1 depends on the current that is flowing through this 3 ohm resistor branch. So to apply Thevenin's theorem in this type of circuit, we have to calculate first the Thevenin's voltage. For this question, only the Thevenin's voltage is asked for now. Like if you are to calculate the R Thevenin in normal circuits, what do? We replace this voltage source by its internal resistance, right? So voltage source goes to a short circuit. But in case of dependent sources, we will keep the sources as it is, and only the independent sources will be replaced by their internal resistance, and that's how it is calculated. We'll see it eventually in one of the problems. So for now in the question it is asked, estimate the Thevenin's voltage between terminal A and B, where A is the positive and B is the negative terminal. So to calculate this, how will we calculate the Thevenin's voltage across this? So all the circuit parameters will be present, and we'll have to calculate the voltage across this. Thevenin's voltage is the voltage across this output terminal, which is equal to VAB. This is what we have to calculate, right? So let us start solving this circuit. Normally how we calculate VAB, exactly like that we will be solving this circuit as well. Only the problem is like this dependent source will be dependent on certain parameters that are already present in the circuit, the unknowns, that is I1 and V1. So like this circuit itself, let us draw like maybe I'll redraw, or no, I'll just use a different color and then we'll solve the circuit. So yeah, so this I1 current is flowing in this branch. So if I apply KCL, let's say this is point C. This node and this node are exactly same because there is no element connected across it. So this is basically kind of a super node. So the voltage across this VC will be same. This is the VC itself. Now if we apply KCL at the node C, so applying KCL at node C. So our ultimate aim is to calculate this unknowns which are I1 and V1, right? Once we calculate this unknown, we'll be able to figure out what is the voltage drop across this terminal AVAB, right? So we first apply KCL at node C. So here this I1 current is flowing into the node, 1 by 6 V1 current is flowing out of the node, and here certain current will flow through the node, whatever the current may be, and here since this A and B are open circuit terminal, so current here will be equal to 0. And in this case, what current will flow through this branch? Because this V1 voltage which is across this 6 ohm resistor, this V1 voltage will appear across here. So the current that will be flowing through it is V by R. So V is equal to V1 and R is equal to 6 ohm. So V1 by 6 current will flow across this 6 ohm branch. So on application of KCL at node C, we will get I1 minus V1 by 6, which is this current source current that is flowing, and the current through the 6 ohm resistor, which is again V1 by 6. Since there is no current flowing across here because A and B are open circuit terminal, this will equate to 0. Is this clear? Everyone following me?
Yes, ma'am. Yes, ma'am.
Yes. 2 V1 by 6, so it is V1 by 3. We get the relation between I1 and V1. Now what we need to do is have another relation with I1 and V1 because these two are unknowns we have. So the second equation, how we will calculate? Any suggestion? Anyone
We can
want?
apply KVL. KVL.
Yes. So we will apply KVL across this particular loop, right? And we will get another relation between I1 and V1. So let's calculate it. So when we apply KVL across this loop, it will be, we will first start from here. So it is 2 volt. Then current I1 is flowing through this 3 ohm resistor. So it is minus 3 into I1. Now through this 6 ohm resistor, V1 by 6 current is flowing, right? So, or you can simply, if you, since the voltage drop across this is V1, so the voltage drop across the 6 ohm resistor is V1, so we can write simply V1 will be equal to 0, right? Because suppose if I redraw this circuit, this loop will be 2 volt, this is 3, current I is flowing, then this current source will be present, and then this 6 ohm resistor. So across this 6 ohm resistor, the voltage is V1. Since this is open circuit, it doesn't matter, no current is flowing. So if we apply KVL across this loop, it will be this 2 volt minus 3 into I, voltage drop across this, and minus the voltage drop which is V1. So this is the second relation that we have. Now if I replace I1 from equation 1, we'll get 2, 3 into V1 by 3 minus V1 equal to 0. So it is 2 equal to 2V1. So V1 is equal to 1 volt, right? So since we have V1, we can calculate I1. I1 will be equal to 1 by 3 amps. So now that we have V1 and I1, we can calculate VAB. So what will be VAB? So let me read out the circuit here itself. So this is plus minus 9I1, and this is A positive side and B negative side. So VAB will be equal to, if we start traveling from this direction, so now to calculate VAB, we will move from this side. So it is, so the current that is flowing here is V1 by 6 through this 6 ohm resistance. V1 by 6 ampere current is flowing, right? So V1 is 1 by 6, right? So the voltage that we will face while moving from to calculate VAB is this V1 voltage, V1 minus 9I1, right? Because the voltage drop across the 6 ohm resistor is V1. So V1 minus 9I1 is the voltage across this terminal AB. We have V1 as 1 volt and I1 as 1 by 3 ampere. So it is 1 minus 2, sorry, 1 minus 3 minus 2 volt. So Thevenin equal to VAB equal to minus 2 volt. Is this fine?
Yes, ma'am.
Okay. Now we have the Thevenin's voltage. Now we have to calculate the Norton's short circuit current between terminal AB. So in the question it is asked, if we short this terminal AB, what will be the value of this short circuit current? So while calculating the short circuit current, we will have to again solve the circuit keeping the dependent voltage source as it is. Now this I1 and V1 will change, because earlier you see this was an open circuit, so no current was flowing through it. So there was the certain value of I1 and V1. Now keep in mind, when you are shorting the N terminals, this I1 and V1 may or may change depending on the circuit parameters. Now this is a kind of a closed circuit and we have to figure out what is ISC, right? So now again we can apply KCL. So here this current ISC is flowing and coming here. So this branch voltage will be V1 by 6 again, because there is no other voltage source connected across this 6 ohm resistance. So the voltage source that is connected across is this 9 I1. So can we write V1 will be equal to 9 I1, because V1 is the voltage across this 6 ohm resistor. Also this voltage source which is connected, since this is short now, so it is basically connected across the 6 ohm resistor itself. So it is like this. This is plus minus 9 I1. Also we know that the voltage across this is V1. So basically the voltage across 6 ohm, these two are the same voltage. So V1 is equal to 9 I1. This is one of the relation that we have. Now to solve, now we have actually three unknowns. We have I1, V1 and ISC. So we need to have three equations. So we will apply KCL and KVL. First let's apply KCL at node A. So, sorry, node C. So let this is the node C. So let's assume that since this V1 voltage appears across the 6 ohm resistance, so basically the voltage in this node is actually V1, right? So we will apply KCL at node C. KCL at C. This gives us, so I1 is the current that is flowing into the branch. Now we will calculate the current. Those are equal to the current that are flowing out of the branch. So the first is the current source, voltage dependent current source current, which is V1 by 6. Then it is the current that is flowing in this particular 6 ohm branch, which is the voltage, the node voltage. This is, suppose, oh, let's say this is the ground one, so it is V1 minus 0 by 6, so it is V1 by 6. And the third current that is flowing out of the node is this ISC current plus ISC. This will be the KCL at node C. Initially, like in the previous case, since we were calculating the Thevenin's voltage, this was open circuit and we did not have this current. Now it is added to it, right? So, so the third equation that, let us simplify this. This is V1 by 3 plus ISC. Now the third equation that we will have here is applying the KVL across this particular loop, right? So the KVL equation that we'll have is, so we will start from this 2-volt source. So it is 2 minus 3 into I1, the voltage drop across the resistor, minus, so instead of this loop we can also go for the bigger loop, since there are no other resistance connected across it, to get the relation with ISC. Since ISC is also present, what we will do, instead of applying KVL at this particular loop, we will apply KVL in this loop, so that we will have an equation with only I1. See, if we apply KVL through the 6 ohm resistor, we might end up with having V1. So let us apply KVL in this bigger loop to just get equation in only I1. See, I1 current is flowing here and there is a relation with I1 here. So it will be 2 volt, the voltage drop across this resistor, the voltage dependent, the current dependent voltage source that we have, which is, since we are entering from the positive terminal, minus 9 I1, and there are no other circuit elements present, so this will be equal to 0. So we can directly calculate I1. Had we taken the smaller loop, we had to again substitute the value and get it. So it is 2 equal to 12 I1. So I1 is equal to 1 by 6, right? So we have I1 equal to 1 by 6, so we can have V1 is equal to 9 into 1 by 6, that is 3 by 2. Okay? So this, now what we can do is, we can calculate ISC, since we have I1 and V3. So ISC will be equal to I1 minus V1 by 3. I1 is equal to 1 by 6, V is equal to 3 by 2 into 3. So 1 by 6 minus, so we'll get it half. So this is 6, 1 minus 3, that is minus 2 by 6, that is minus 1 by 3, which is it. So therefore the short circuit current will be equal to minus 0.33 ampere. Is this clear? So we have calculated the Norton short circuit current between IAB in the direction from A to B. So this is this short circuit current IAB. Okay. Now in the next part of the, yes, there is some echo, I think. Okay. So estimate the Thevenin's resistance between terminal A and B. So we have the Thevenin's voltage across A and B, and we have the short circuit current between A and B. In case of in order to calculate, in case of dependent sources, R Thevenin can be calculated by V Thevenin by I short circuit current, right? So V Thevenin we had calculated in the previous question to be minus 2 volt. So it is minus 2 volt, and the current that we have calculated here is minus 0.33 ampere. So the minus 0.3, let's not write minus 0.33, we'll write it at minus 1 by 3. So, okay, minus 1 by 3. So this will be equal to 6 ohm. So the Thevenin's equivalent voltage for this circuit is 6 ohm. Is this okay with everyone? Everyone following up to this much?
Ma'am, how is V1 equals to 9 into I1, ma'am?
Okay, so just consider this much part of the circuit. So let me take a different page. So you see, in the second case, what you were told, like this AB is short circuited, right? So there is a connection between A and B. This is the short circuit current. So between, suppose let this node be node C, okay, and this node be node A. Since there is no other element connected between O and B, this particular node is also node O. Since there is no other element connected across A and B, this particular node is also node O. So basically, I can redraw the circuit like this. So, so this part of the node C, here there is no element connected, so this is node C. So one point of the voltage source, the positive side of the 9I1 voltage source is connected to C, and the negative part of the voltage source, here it is connected to actually O, which is the common node, right? So this is O. So V1 by 6, this is 3, this is the voltage, which is 2 volt. So this is the 6 ohm. So across 6 ohm, this V1 voltage is given, so this is equal to V1. So you can, so this is the node C and this is the node O. So voltage VCO is equal to V1, right? Again, this node itself is also C, this node itself is also O, because there is no element connected across it. So again, from this we get the relation VCO is equal to 9I1, right? Because 9I1 is the voltage of this current dependent voltage source. So if we equate this to, we get V1 equal to 9I1. Is this clear?
Yes, ma'am.
Okay. Anything else? Are you clear on how to apply Thevenin's theorem across dependent sources like this when the circuit has dependent sources? We'll be solving another problem later on based on Thevenin's theorem, just to brush up. If this is fine, then we'll move to the next question.
Yes, ma'am, this is fine.
Okay.
It is okay, ma'am.
So for the next question, it is just a simple circuit is given where this is a current dependent current source, and this I current is the branch current that is flowing across this R1 resistance. R1 and R2 are unknown right now. So the question here is calculate the branch current I. So like to get this branch current, how will you do it? The voltage across this R1 resistance is given, right? And the current flowing through this R2 resistance is given, which is 34 ampere. So since R1 and R2 are not known, but the voltage across R1 is given and the current that is flowing here and in this two particular branches is given, We can apply KCL at this node, right? Let this
Ma'am,
node be. Yes?
KBL, KBL.
Yes, we can apply KVL first in this particular loop.
Yes,
So,
ma'am.
to apply KVL, we either have to assume a voltage across this node AO, right? Because R2 is unknown right now. So the best option would be, since this current I1, this is I, this current branch current I1 is given flowing through it, and we have the current in this particular branch and this particular branch too. So we have the 3 branch current. The best option would be to apply KCL at node A and calculate I, because the first, your main aim is to calculate I, not the node voltage at this particular node, right? So you have the branch current in this node, you have the branch current 34 ampere in the second branch, and in the third branch current 0.7 I is flowing. So KCL would be a better option, right? If you apply KVL, you will have to assume a voltage and solve for the unknown again. So let's apply KCL at node A. So if we apply KCL, it will be I current flowing in, 0.7 I also flowing in, and minus 34 ampere flowing out, right? So this is 1.7 I equal to 34. So the current I is equal to 34 by 1.7. So this will be equal to 20, because this is 340 by 17, right? So we have solved for I. So this 20 ampere current is flowing in. Now you are asked to find the power supplied by the independent source and the dependent source. So which one is the independent source here?
0.7 I.
No, independent. Independent means it is not dependent on any other parameters of the branch.
15 volt.
Yes, because it is independent. Its value won't change if any other branch parameter is changing. So the dependent source here is 15 volt. So to calculate the power supplied, why supplied? Because current we have obtained is 20 ampere, which is positive. So 20 ampere current is flowing out of the voltage source, which means coming out of the positive terminal. So it is supplying the power. So the power across this 15 ohm resistance would be V into I, right? So the voltage is given as 15 volt. The current we have calculated to be 20 volt. So it is 300 watts. And then you are asked to calculate the power of the dependent source also. So how we are going to calculate the power of the dependent source? So in this case, the dependent source is the current source, right? Which is 0.7 I current source. So we have to find the power. So what do we need for power? Voltage and current, right? We have the current that is flowing here. So what will be the current? Current through this 0.7 ampere current source, it will be 0.7 into 20, right? It is 14 ampere. And to get the voltage, we will have to solve the voltage, node voltage VA, right? So let us just assume the voltage across 0.7 I is V. Now as we were saying, we will apply KVL. So we will apply KVL across this loop. So whatever the voltage that will appear across this 0.7 I current source will actually be the voltage across this VAO, right? So if we consider this this plus, so VAO is equal to VAO, sorry, voltage that we have assumed across this 7I current source. So even if we so when we apply KVL in this shorter loop, we'll be able to calculate what is this voltage V. So applying KVL through the loop, we get 15 minus the voltage drop across R1 is given as 9 volt, and we have assumed the voltage AO to be V. So it is minus V will be equal to 0. So we have V equal to 15 minus 9, 6 volts. So this same 6 volt AO, since this node is also A and this node is also O, this same 6 volt is appearing across this 0.7 I current source. So here the power will be 6 into 14. So 6 into 14 is 84 watts. So the power that is supplied, since we got the voltage to be positive, so it is in this direction and the current is going out of the positive terminal. So this particular source is also delivering power. Is this fine?
Yes, ma'am, it is fine.
Any questions?
No, ma'am.
Okay. Now calculate R1 and R2. So I'll just write it. This is 14 ampere current. This is 20 ampere current. The voltage across this is 6 volt. Now we have to calculate R1 and R2. So you have the value between, so the voltage across this and voltage across R2 will be same, and we are given the current, so we can easily calculate the R2 unknown resistance, right? So it is 6 volt by 34 ampere current is equal to R2, right? R2 will be equal to 3 by 17. And for R1 we have the current and the voltage across it, so we can calculate easily R1, right? R1 will be equal to 9 by 20, right? 0.45 ohm. So right now you don't have to do it. Later on you just check, like since this is also delivering power and this is also delivering power, the entire power will get dissipated between R1 and R2. So the net power, that is I square R. So if you do I square, that is 20 square into R1 plus 34 square into R2. This will equate to the total power that is getting delivered, that is 84 plus 300. So it will be, this will equate to around 384. Just do it later on as a part of your practice, just to check that the entire power that is getting supplied by the two different sources is getting dissipated in the resistor. Okay. So if this is fine, then we will solve, we will go to the next question. Shall we move on?
Yes, ma'am. Yes, ma'am.
Okay. So again another circuit is given and you have to calculate I1 and I2. So instead of applying any theorems, we can also simply straight away solve this circuit, right? So how shall we start to solve the branch currents I1 and I2 here? Any suggestion? We have to solve for this current that is flowing here, I1 and I2. Now this voltage source, this is a current dependent voltage source which depends on this particular I2 current flowing in this particular branch. So how shall we solve for I1 and I2 for this circuit?
Now apply KVL at
Ma'am,
node
KCL.
So
KCL.
KVL, so yeah, using KCL we will determine the current in this branch. So I1 current is flowing in this particular branch, I2 current is flowing in this particular branch. So in the third branch, the current that is flowing is I1 plus I2 using KCL. Now we will apply KVL in the two loops and we'll get two different equations and we can calculate I1 and I2, right? So KCL in the first loop. So it will be 20 minus, we come across this 20 I2 resistance, so it is 20 I2. Then it is through,
Ma'am, it is KVL at loop 1.
yeah, KVL, sorry, KVL at loop 1. So it is 20 minus 20 I2, then minus 20 into the current that is flowing is equal to I1 plus I2. Then again this same current I2 will be going here and I1 will be going here, because I1 plus I2 current is coming out. So through this 30 ohm resistance we have again current I1 flowing. So it is minus 30 into I1 equal to 0. This is one of the equation. So this is equal to 20 minus 20 I2 minus 20 I1 minus 20 I2 minus 30 I1 equal to 0. So if we simplify this, it is if we take the I1 and I2 on the other side, so it will be I2 is 40 I2, then I1 is 20 30, so it is 50 I1. This will be equal to 20. This is the first equation. Then again applying KVL at loop 2. So if we are moving in this particular direction, let's say, so it is 15 volt minus 20 I2 minus 20 I1 plus I2 equal to 0. So if we take the constant on that side, so it will be 20 I2 plus 20 I2, so it will be 40 I2, and I1 is just 20, so 20 I1 will be equal to 15. This is the second equation. So if we subtract 1 and 2, we can get rid of this 40 I2. So 1 minus 2 will equate to, so 50 I1 minus 20 I1 is 30 I1, and I2 will get cancelled, and 20 minus 15 is 5. So I1 equal to 5 by 30 or 1 by 6. So we can plug this I1 to any one of the equation and calculate I2, right? So let's plug into the first equation. So it is 50 by 6 plus 40 I2 is equal to 20. So 40 I2 will be 20 minus 50 by 6. So this will be 70 by 6, right? Yes. So I2 is equal to 7 by 24. So whatever the values may be. So 1 by 6 will come out to be 0.666 something ampere, right? What is this 7 by 24? Let's calculate 0. So it is 0 0.2916, something like this. So we have solved for I1 and I2. So no matter how like big the circuit is, only difference for this dependent sources will be that it will depend on certain branch parameters, which may be a current or voltage. Otherwise the like solution of the circuit will be exactly how we do it for any normal circuit. So let's look into another problem. So the fourth problem that is given here is we have to estimate the electric power supplied or generated by the independent sources. Here how many independent sources are there?
Only one.
Yes, this is the 6 volt independent sources. So we have to calculate the power. So there are second part of the circuit will be for the dependent sources too. So we will first solve for all these branch currents and voltages, and we will finally calculate the power. So if we look into the circuit where the 6 volt voltage source is connected across the 10 ohm resistor. So can you tell me from the circuit how are V1 and V2 related?
Both are
It's
same.
same.
Same,
Same.
right? So since there are no element connected between them, so V1 will be equal to V2. And if we look at V4 and V5, they are also the same thing, right? V4 and V5, nothing is connected between them. So V4 equal to V5 will be equal to what? This particular voltage source that is connected. Here this voltage source is given as 8I2, right? So this will be equal to 8I2. Now in order to, so V1 equal to V2 and V1 is equal to 6 volt, which is this particular voltage source. So V1 equal to V2 equal to 6 volt. We have this. So now we have to calculate V3, V4 and V5. So for that, let's first, since the okay, so we can calculate V3, right? The current that is flowing across this particular branch. So here this current, this I3 current, which is also flowing across this branch, this is the same current. So I3, which is equal to the current that is flowing across this particular branch in which this current source is present, is 8 into V1. We have the value of V1, so it is 8 into 6, 48 ampere. Now can we calculate I1 and I2? What will be the value of I2?
V1 by 10.
Yes, V1 or V2 by 10. And we have V1 already equal to 6 and this is 10, so I2 equal to 0.6 ampere. So now can we calculate I1?
1 ampere.
Sorry?
No, no, ma'am, no.
So to calculate I1, we can apply KCL here, right? Can we apply KCL at this particular node?
Yes, ma'am. Yes.
So it
Yes,
will
ma'am.
be
Yes,
I1
ma'am.
equal to I2 plus I3.
48.6.
Yes. So we have solved for I1, I2, I3, V1, V2, and we can calculate V3 now. So V3 is the voltage. So right now, since we do not know what will be this node voltage, which is equal to V4, which is again dependent on 8I2. So let's calculate V4 and V5 first. So now we have the value of I2 here as 0.6. So we can calculate 8 into I2, right? So 8 into 6, 0.6. So it is 4.8 volt. So we have V4 and V5. So now can we calculate V3? What will be the value of V3? At this particular node, the voltage is either V1 or V2, which is same. At this particular node, the voltage is either V4 or V5, which are both equal. So what will be the value of
Is it
V3?
1.2, ma'am?
Yes.
1.2?
So it is V1 minus V4. So 6 minus 4.8, 1.2 volt, right? So we now have I1, I2, I3, V1 and all the voltages. Now we can calculate I4 and I5, right? So I3 current, I3 which is equal to 48 amps is flowing into this branch. And we have, since we have V5, we can calculate I5. So I5 will be equal to V5 by 8, this resistance and the voltage across this resistance. So V5 is 4.8 and sorry, this is V5 by 5, right? The resistance is 5 volt. So this is 0.93, so it is 6.96 amps. Now can we apply KCL again at this node and calculate I4? We have the value of I3. So at this particular node, we have I3 equal to 48 amperes going in. We have I5 0.96 ampere going out, and we can calculate this I4. So I4 will be equal to
I3
I3
minus
yes. So it will be I3 minus I5.
I5.
I3 is
47.04.
yes. So it is 47.04. So now we have all the values of current and the voltages. So now we can calculate the power generated by the dependent and the independent source. Since in this question first it is asked for the independent source, now what will be the power generated by the independent source?
V1 I1.
V1 into I1. We have
6 I.
V1 as 6 volt and I1 as 48.6. So this will be equal to 6 1 291.6 watts, right? Now we have to estimate the power supplied or generated by the dependent sources. So V1 equal to V2 equal to 6 volt, V3 equal to 1.2, V4 equal to V5 equal to 4.8, and the current are where is I1? 48.6. So this is 48.6, I2 is 0.6, I3 is 48, I4 is 47.04, and I5 is equal to 0.96. Okay. So can you tell me what is the, let's take the current source first. So power supplied or generated, please note into the fact it is written supplied or generated by the dependent voltage source. So let's say this current voltage current dependent sorry voltage dependent current source, this particular current source, what will be the power delivered by this? So what will be
V3
it?
into I3.
V3 into I3. So V3 is 1.2, I3 is 48. So this will be equal to, let me just calculate.
But ma'am, it is observing power.
Yes, I'm coming to that.
Excuse me, ma'am.
Yes,
That current source, the 8 mho V1 is given.
yes,
So it does matter. It is a that ohm or mho.
yes. Like so, let's look into this current source. So this is a voltage dependent current source, right?
Right.
So it is given as 8 mho into V1. So what is V1? V1 is in volts,
Right.
right? And 8 mho means 1 by R. So this I equal to V equal to IR relation has to be there. So I will be
Right.
equal to V by R. So unit of V is volts and unit of R is ohm. So if I am to take this inverse, inverse is basically ohm is inverse of mho. So this current dependent voltage source has to be always of this unit, mho into V, right?
Right.
Now in this case, like so that is clear, right? So now for generation of power, so we have current that is flowing in this direction, and the voltage drop V3 we have calculated it to be positive 1.2 volt, right? This means current is coming out of the negative terminal or going inside the positive terminal, which means this is actually absorbing power, not generating power as mentioned in the question. So in order to calculate what the power is getting generated, what we can do is we can only assume that a minus 1.2 voltage drop is across this particular current source, right? So we just changed the positive and a negative terminal. Now the current is coming out of positive terminal, which is basically now delivering power, but the voltage had to be, we had to use a negative sign, because if there is a plus voltage drop across this 1.2 volt, if we reverse the like polarity of the terminal, it will be minus 1.2, right? So since we are asked the electrical power that is supplied or generated, we have to take minus V3 instead of V3. So it will be minus 1.2 into 48, which is minus 57.6. Had the question been how much electrical power is absorbed by the voltage source, we would have taken it to be 57.6 watt. Since it is mentioned as specifically as supplied or generated, it is coming up with a negative sign. Is this clear?
Yes, ma'am, it is clear.
Yeah. Now the next, this is done. So estimate the electric power supplied or generated again by the dependent voltage source, which is this particular voltage source. So now can you tell me what will be the power supplied or generated by the voltage source?
Again, it is entering positive, so we have to put minus V4.
Yes. So in this case it is again entering, so either change, reverse the direction of the current or reverse the direction of the voltage. So if we reverse the direction of the voltage, so it will be, so we had this equal to V4. V4 is 4.8, I believe. Yeah. So this is 4.8 volt initially. So if we reverse the polarity, then it is minus 4.8 volt. Now it is delivering power. So it is minus V4 into I4. That is minus 4.8 into I4 is 47.04. So this will come out to be negative something. Let us just calculate it. So it is minus 225.792 watts, right? In the
Yes, ma'am.
third, in the third case, it is asked. We have done this. So in the third case, it is asked estimate the electric power consumed or dissipated by the two resistor. So what will that equal to be? Total power consumed or like dissipated by the resistor will be the power dissipated by the 10 ohm resistor and the power dissipated by the 5 ohm resistor. So power dissipated is can be written as, it can be I square R, it can be V square by R, whatever you wish. Let us write into as I square R. So for the 10 ohm resistor, I2 current is flowing in, and in this case you observe
Ma'am,
V2.
can we write it as V2 into I2?
Yeah, I guess it will be the same thing, V2 into I2.
Yes, ma'am. Okay, okay, okay.
So let's write into V2 into I2 itself. So V2 is 6, I2 is 0.6. So 6 into 0.6. In this case, the current is going inside the positive terminal. That means it is absorbing or consuming power. So this is fine, no problem with the sign. Now the current through the 5 ohm resistor is, like we can also write like V5 into I5 or I square, like I5 square into 5, or we can write V5 square by 5, whichever way, like it will be the same answer. So in this case too, the current is entering through the positive terminal, so it is consuming power, or like it is dissipating the power, so it is positive. So this will be equal to I5 into V5. So I5 is 0.96 and V5 is 4.8. So can you quickly calculate the total value? So it is
4.608.
okay. The total, are you talking about the total power?
No, ma'am, no, ma'am.
Okay.
It is by 5 ohms.
Okay, okay. So let us just calculate it. So it is
Total is 8.208.
okay. 4.608. So total is 8.208, right? Yeah. So this is the total power that is getting dissipated by the two resistors. Okay. This, I hope this is clear to everyone, right?
Yes,
Yes, ma'am.
ma'am. Yes.
Okay. Now let's move to the next question, where again this is, we have to calculate the Thevenin's equivalent voltage and resistance for this particular circuit. Since we have already solved one problem on this, so one of you or any one of you will assist me how to go about solving this, right? So to solve, we will calculate the Thevenin's voltage at first, and then we will calculate the resistance by short circuiting this terminal AB. So the steps are: first calculate the Thevenin's equivalent voltage in which all the sources are present, then calculate the, now like either assume a current, short the terminal AB and assume a certain current I flowing through it. So you have the voltage across this terminal AB and the current. So in case of dependent sources, R Thevenin is calculated by open circuit voltage, where in this
By
case,
short circuit current.
yes. So these are the steps. So let's start off by calculating VTH. So what do we do about this circuit to solve the voltage? Here you see the voltage across this terminal. Let us consider this to be positive, this is to be negative. So from the given node voltages, V1 is the node voltage in this node, V0 is the node voltage in this node, this is the reference node. Can you tell me what will be VAB in the circuit?
Ma'am, 8ix.
V0, ma'am.
Yes. So since this is the node voltage and this is ground, so V0 minus 0 by, so voltage will be V0 minus 0. So this will be equal to V0. Now, as one of you said, like since this is an open circuit, so there is no current flowing in this circuit. So whatever this Ix current is flowing, it is coming through this particular branch itself, right? So V0 will be equal to
IX
8,
into 8.
8
right,
into Ix.
right. So we will apply a KVL equation across this loop, and like figure, let's see like how many unknowns we have. Since we have V1, V0 and Ix, we will look into the unknowns, and eventually we will see whether we have to apply KCL at the nodes to calculate them. So so first like in this particular node, since the current is given in this particular branch Ix into 1.5, and there is a current given in this particular branch which is equal to Ix, we can calculate the current flowing in this particular branch applying KCL at V1, right? Once we know this branch current, this particular branch current, it will be easy to apply the KVL through this bigger loop. So we will apply KCL at V1. So when we apply KCL here, how will we, what will it be? The KCL equation?
Tall minus V1 upon 10 plus 1.5 Ix is equal to Ix.
Yes. Now, so after that, we can simplify this equation.
Ma'am, there is one more option.
Sorry?
There is one option. We can find current in 10 ohm resistance very easily since current source is Ix 1.5.
Yes.
Ix is going this side in 6 ohm, so it
This
means
is
in 10 ohm.
0.5 Ix,
Yes, yes, yes.
right?
But
Yes.
reverse direction, reverse direction.
Sorry. Yeah.
So, and from that we can apply KVL and very easily calculate Ix.
Yes, yes, exactly. So we will look for the shortest way out. We don't really need the node voltage in order to calculate the Thevenin's voltage. So no point involving, sorry, no point involving V1. So we apply KCL at V1. Whatever, let this current be I. So I plus 1.5 Ix will be equal to Ix. So I will be equal to minus 0.5 Ix. So since we have assumed I in this direction, it will actually be in the reverse direction. So we will get, sorry, we will get current in this direction 0.5 Ix, right? Now we can directly apply KVL in this bigger loop. So when we apply KVL, so we are moving from this direction, so 12 volt, so current is moving in this direction, so basically the voltage drop will be in this direction, so it will be plus 0.5 Ix into 10, right? Then the voltage drop across the 6 ohm resistors, which will be equal to 6 into Ix minus 8 into Ix will be equal to 0. So this is a equation only in Ix. So we can directly solve Ix. So it will be 12. If we take all of this in this side, it will be minus 5 Ix. 6 plus 8 is 12 Ix equal to 0. Sorry. So 12 minus 5 is, sorry, 6 plus 8 is 14, not 12. So 14 minus 5 is 9 Ix. 9 Ix will be equal to 12. So Ix will be equal to 4 by 3. So we have solved for Ix, and the only thing that we need to find the Thevenin's equivalent voltage across AB will be equal to 8 into Ix. as we have seen here. So since the current will be flowing in this direction, the voltage drop will be along this direction. So VAB equal to VA equal to 8Ix, which will be equal to 8 into 4 by 3. So the Thevenin's equivalent voltage is 32 by 3 or 10.20. So it is 6, carry over to 6, 7, 10.667 ampere. Sorry, volt. This is the Thevenin equivalent voltage. Now we have to calculate the short circuit current. In order to calculate this short circuit current, what we will do is we will assume a current flowing through AB. So what we will do is the dependent sources will be shorted. For voltage source, we will replace it by their internal resistance, which is a short circuit. The independent source, we will keep it as it is. So the new circuit, in order to calculate the R Thevenin, will be something like this. So we will just assume whatever the voltage here will be equal to V Thevenin, right? So what we will do is we will give a 1 ampere, I equal to 1 ampere current source across this terminal AB, and we will keep the rest of the circuit as it is. It is 1.5 Ix. The independent sources, for example in this case this voltage source, it will be replaced by the internal resistance, which is basically a short circuit. This is the 10 ohm resistor, this is the 6 ohm resistor, this is the Ix, that current that is flowing here, this is V0, this is V1. In this case what we do, like in the earlier one we had calculated the short circuit current, right? Instead of that, what we did here is we connected a 1 ampere current source across this. Now we will calculate VAB and we will be able to figure out R Thevenin, which will be equal to the voltage across VAB and the short circuit current that we are instead of short circuit current we are applying this current source, which is equal to I, which is equal to 1 ampere. This will be equal to R Thevenin, right? Is this clear? Now we solve this particular circuit in order to calculate VAB. VAB will be equal to V0 basically. This will be equal to V0. So this is the 8 ohm resistance. Now note that since the voltage source is not present, Ix value may change, V0 value may change. We will calculate it accordingly. So now our main aim right now is to calculate Ix, because see in this branch Ix current is flowing in. I'll take a different color maybe, wait. So this Ix current is flowing in. This 1 ampere source that we have given, 1 ampere current is flowing in. So by using KCL at V0, we will get the current flowing here is, what is the value? If we apply KCL at node V0,
1 plus Ix, 1 plus
right?
Ix.
Yes, it is 1 plus Ix. Now in this particular branch, what will be the current? So Ix current is flowing out, 1.5x current is flowing in. It is again what is the value in this particular branch? The current
0.5 Ix.
It still remains 0.5 Ix in this particular direction, right? So we have the branch currents for all of this. Now we can apply KVL across this bigger loop, right? So this is the we can either apply KVL or we can simply look into the circuit and see whether we can further, simplify it. For example, is there any relation between the branch voltages or currents, etc.? So let's try that first. For example, in this particular branch V0O, so V0O or V0, this branch voltage will be equal to 8 into I1 Ix into Ix plus 1, right? Because this will be the voltage drop across this 8 ohm resistance, right? This is the same node voltage. This is fine, right? Is this fine?
Yes, ma'am. Yes, ma'am.
Okay. Now, if we apply KCL at node 1, let's say KCL at node V1, by KCL we had calculated this current Ix, right? We can also write in terms of voltage, like that is voltage at node 1, that is V1 minus 0 by 10 plus, so all the currents, these two currents, Ix currents are going out, so it is plus Ix. This will be equal to 1.5 Ix. So we have a relation between Ix and V1. So it is V1 by 10 equal to 0.5 Ix or V1 equal to 5 Ix. Now we need to have another equation which is relating V0 and V1, or which is relating V0 and V1. So can we write that? How will we write the relation between V0 and V1?
V1 minus V0 is equal to 6Ix.
Yes. So it is the voltage across this particular node, this particular node. So the current flowing through this node is Ix. I into R is equal to the voltage drop across it, which is V1 and V0. Now, in order to calculate VAB, we need to find the value of V0. So we will we will keep V0 and substitute rest of the values. So what will we do is, suppose like in this equation we will substitute the other values. So so V1 is equal to 5Ix. Let this be equation 1, this be 2, and this be 3. So in 3 we are substituting equation 2. So in place of V1 I am putting 5Ix minus V0 equal to 6Ix. So V0 will be equal to minus Ix. Let this be 3. So substituting in equation 3, we get V0 equal to 8. In place of Ix, we will put minus V0 plus 1. So 9 V0 is equal to 8. So V0 will be equal to 8 by 9. So VAB is equal to VA0. So we have VAB is equal to V0 will be equal to 8 by 9. So can we calculate R Thevenin now? What will be the value of R Thevenin?
8 by 9.
Yes, it will be equal to 8 by 9 by 1, which is equal to 8 by 9. So we had calculated the, did we calculate the VThevenins? No, right? We had, let me just check. So in the previous, yeah, we had calculated VAB. So now we have the Thevenin's equivalent circuit, where VThevenin is equal to 10.66667 volt, and there is a resistance of 8 by 9. So it is 0.889. This is the Thevenin's equivalent circuit in case of this dependent, when in the presence of this dependent source. Is this fine? the first problem that I showed, what I had done is we had short circuited the terminal A and B and calculated the Norton short circuit current and then calculated the R Thevenin. In this case, what we had done is we had like connected a 1 ampere source and calculated the voltage across AB in order to calculate this R Thevenin. So whichever makes your circuit simplified, you can use either of the two. Is this fine?
Yes, ma'am. Yes.
Okay. Then we'll look into another problem. Now that we are familiar with Thevenin's theorem, let's do one with superposition theorem. So all the network theorem has to be applied for this kind of network. So in case of superposition theorem, what we used to do earlier when there was no dependent sources, only independent sources were present, we would take one source at a time and calculate its contribution, whether be it branch current or branch voltage, and we used to add up. For example, if suppose if this 3i source, dependent source, would not have been present, what we had done, once taken the 24 volt source, then taken the 7 ampere current source and shorted the other depending on replace the other one by their internal resistance and calculated the contribution. Like for example, in this case it is I1 dash, this is I1 double dash. The final current I would have been equal to I1 dash plus I1 double dash. But when the dependent sources are present, we would do the same thing, except for the fact for this dependent source we will keep it as it is, as we have kept in case of the Thevenin's theorem. So in all this network theorem, what we are doing is the dependent source we are keeping it as it is. So how will we solve this? See, this is the simplest problem in network theorem. When it will get complicated, this type of network theorem will make it more easier to solve the circuit. So for example, in this case, to calculate this unknown parameter, which is the branch current I, we will do first we will consider this 24 volt source and we will replace the current source by an open circuit, that is their internal resistance. So we will take this 24 volt and calculate in this case, let us name it as I dash. This current source is open circuited. The 2 ohm resistor is present as it is. Please note that now what we will do, so this particular current dependent voltage source depends on the branch current I through this 3 ohm resistance. If this I changes, this value also changes. Now that we have taken I dash here instead of I, because the total I will be a contribution from this 24 volt source and this 7 ampere current source. So for now this is I dash. So instead of writing it 3I, we will write 3I dash, because whatever the branch current will be here, that same current, this current dependent voltage source will change accordingly. So we will take it as 3I dash. Now we will simply since we have the current flowing here and we have the two voltages, we can easily apply KVL in this loop. So it will be 24 minus 3 plus 2, 5I dash. 5I dash minus 3I dash will be equal to 0. So 8I dash will be equal to 24. I dash will be equal to 3. So for this 24 volt voltage source, a current of 3 ampere is flowing through it. Now the same thing we will do using the current source. So now what the circuit will be? So now the current source is considered, the 7 ampere current source. The dependent voltage source will remain as it is. So sorry, there is this 2 ohm resistance, there is this 3 ohm resistance. Now the voltage source is short circuited. Whatever the current I double dash will be flowing on it, what will be the value of this voltage dependent source now? 3I double dash, because it depends on the branch current that is flowing through this 3 ohm resistance. So now we have the branch current from here, which is I double dash, and 7 ampere current is flowing here. So we can calculate the current through this 2 ohm resistance, right? So it will be 7 plus I double dash. Now we can apply KVL in this big loop, right? So it is 3I double dash. So we are going against the current, so it will be 2 into 7 plus I double dash plus 3I double dash will be equal to 0. So this is 3 plus 2 plus 3, 6, 7, 8. 8I double dash will be equal to minus 14. I double dash equal to minus 7 by 4. Right? So the net current flowing I will now be equal to I1 dash plus I1 double dash, which is 3 minus 7 by 4, which is 12 minus 7 is 5 by 4. So the net current that is flowing across here is 5 by 4. Just to get a feel of whether we have done it right or not, let us quickly solve this circuit directly for I1. So let us for this particular circuit itself, uh, 1 second. Since this is a very simple circuit, we can solve it normally for I. So here I current is flowing here, 7 ampere current is flowing here. So we have 7 plus I current flowing through this. Now we apply KVL. So it is 24 minus 3I minus 2 into 7 plus I minus 3I will be equal to 0. So it is 24 minus 3I, so minus 6I minus 8I minus 14 will be equal to 0. So 8I will be equal to 10, I equal to 5 by 4, which is exactly what we had got when we used superposition theorem. Are you getting the feel of this?
Yes, ma'am. Yes.
Okay. So this is how we apply superposition theorem in these circuits. So can we, like for this circuit, can we use superposition theorem to solve it, since we solved in the previous one? Can you let us do this one together? So first what we will do, we will only use superposition theorem to solve this circuit. So first what we will consider,
30 volt.
let us consider the 30 volt current source. So this is the 6 ohm. What will be the current dependent current source? Like let's say this is 4. So for one we will write is I1 dash. So this is 2 ohm, this is 4 ohm. This current source will be open circuited. What will be the current flowing through this current dependent current source?
8 I1 dash.
Right. So we have to now figure out I1 dash. So I1 dash current is flowing here. 8 I1 dash current is flowing in this branch. What will be the current in the 6 ohm resistance?
It would be 9 I1 dash.
9 I1 dash. So now we can apply KVL in this loop to solve for I1 dash. So it is 30 minus 54 I1 dash minus 4 I1 dash minus 2 I1 dash will be equal to 0. So 50, this is 60 I1 dash will be equal to 30. So I1 dash equal to half. Next, what we will do? What is the next step for superposition theorem?
We will short circuit 30 volt and use
Execute voltages.
Yes. So we will keep this 3 ampere current source, short circuit this. Now let this be I1 double dash. So the current here will be 8 I1 double dash. So we have the branch current here 8 I1 double dash. We have the branch current here 8 I1 double dash. What will be the branch current in this 4 ohm branch? What will be the current flowing through this 4 ohm resistor? Anyone?
What?
What will be the current that is flowing in this 4 ohm resistor now?
it will be 9 I1 double dash minus 3.
Uh,
10 I1 dash.
Sorry? The current that is flowing in this 4 ohm resistor. This 4 ohm resistor.
I1 double dash minus 3.
Right. If we apply KCL at this node, so 3 ampere current is going in, I1 double dash current is going out. So the net current here will be 3 minus I1 double dash, right? In this particular direction. Right? So now tell me the current flowing through this 6 ohm resistance. For that, what we will do, you will apply KCL at this particular node, right? So what is the current flowing through this 6 ohm resistance? Can you please tell me?
7 double dash minus 3.
Uh, uh, Please take into note the directions. I think you're missing something. Just think like this. So this branch is there, this branch is there, this branch is there, and this branch is there. 4 branches are there. I would really like you to try because like circuit solving will be pretty straightforward applying KCL and KVL. Calculating the correct, like applying KCL correctly is the major issue, right? You will have to figure out the currents.
Ma'am, only 7 double dash.
Are you sure?
Yes, ma'am. I think.
Anyone else got the same answer or different answer?
Is it 9 I1 double dash?
Yes. So let's see. So these are the 4 branches that is connected. 3 ampere current is flowing out. 3 minus I1 double dash current is flowing in, and here 8 I1 double dash current is flowing out. Let us just like assume this is I6. Suppose this is I6. So what will be I6? So current going in, let's take it positive. So I6 plus 3 I1 double dash, these two current are going in, so let's take it positive, and the current that are going out, let's take it as negative. 3 minus 8 I1 double dash. This will be equal to 0, right? So I6 plus, so this 3 minus this 3, this will get cancelled. So it will be minus I1 dash and minus 8 I1 double dash. This is 9 I1 double dash will be equal to 0. So I6 will be equal to 9 I1 double dash. In case you are not able to figure out, please write it in form of an equation and just solve it. That way you'll be able to get the correct value. Don't make a mistake here, because if you end up making a mistake here, and your entire process will go wrong and you will end up with the wrong value even after putting so much effort into solving. So we have now figured out all the branch currents, so we can apply KVL in this particular loop to calculate I1 double dash, right? So tell me the KVL equation here through this particular loop. Tell me the KVL equation. So first we will move through this 6 ohm resistance, right? So anyone, can you start telling me the KVL equation?
minus 6 into 9 I1 double dash
Hmm.
plus
Hmm.
4 into 3 minus I1 double dash
Yes.
minus 2 into I1 double dash is
Yes.
equal to 0.
Equal to 0. This will be the KVL equation. So now we'll just solve for I1. So minus 54 I1 double dash plus 12 minus 4 I1 double dash minus 2 I1 double dash will be equal to 0. So it will be 60 I1 double dash, it will be equal to 12. So I1 double dash will be equal to 1 by 5. So we have so now the net I1 will be equal to I1 dash plus I1 double dash. So we will calculate I1 will be equal to, so I1 dash is half, I2 double dash is equal to 1 by 5. So if we just take an LCM, so it is 7 by 10 or 0.7 amps. Is this clear?
Yes.
Yes, ma'am.
Okay. So like all the dependent voltage source like circuits are like right now it's pretty straightforward. So as the circuit grows bigger, like these network theorems will actually help into figuring out the branch voltages, as we had seen previously when there was no dependent sources, only independent sources were there. For dependent sources, the only thing is the dependent source is retained, whereas the independent ones, it is replaced by their internal resistance in case of using any theorems as per the rules. So this is how basically you will have to solve it. If you have any specific doubt, you can ask. Otherwise, this is pretty much it. Like since sir had not solved an example of superposition theorem, I have given out the just to get the feel of it, the two superposition problems. So anyone has anything to ask? Otherwise, we can like wrap it up for today. Any queries?